All right, deriving the step response RL, deriving the formula for the step response of an RL circuit we're going to have an almost identical setup to what we did for the RC of our resistor, then a switch, a voltage source, then our inductor of inductance L, close our circuit. So this is L, R, here's our polarities, and the voltage at the source Vs closes at t equals 0. At t equals 0. Alright, so this is what we mean by the step response of an RL circuit. We're looking at the time greater than 0, and at this point, instead of in source free just having the inductor and the resistor, because this is what source free circuits look like, now we have a source over here, Vs. The switch is open at t less than 0, so our source is not active, but our inductor is going to have an initial current, which we're going to call I0. Okay, so the way we work around, like I said, for the step response of an RL circuit, the way we work around having to open or close this switch is using the unit step function, which is a mathematical tool, okay, to tell us, oh, at this time, at t less than 0, the source is inactive, or at t greater than 0, the source is active. Okay, so that's L. This is still R, and this, instead of being just Vs, the voltage at the source, we're going to have Vs U of t. All right, remember what we said? U of t is 0 for t less than 0 and 1 for t greater than equal to 1. So that's essentially the setup for the problem. So to derive the expression for the step response RL is going to be far simpler than it was for. Okay, let me redraw this. It's going to be surprisingly simpler than it was that for RC, because instead of working from first principles this time, we're going to use what we know about the nature of the RL circuits. So we wouldn't have to, there's no integration to derive this. Let me wrap this up. Voltage source, close up, inductor L, resistor R, Vs U of t. Okay, and this is inductor current I flowing this way. All right, so what do we know? We know that the response of the way this RL circuit is going to respond once we apply a source is going to look something like this. Okay, so if we were to watch this over time, we're going to have a decaying exponential, and then it's going to even out at a particular value. All right, so these are the two. This isn't clear. These are the two major points of our response. Okay, so this is V, this is time, and if we divide this into two, we're going to see that we're going to have two major parts. Let's call this 5 time constants. All right, so this is 0. So this beginning part is our decaying exponential. All right, where the initial current stored in the inductor is still active in the circuit, and it's going to reduce over time. And then at this point, so this is, let's say this is I0. Okay, and this is IS, the currents infinitely far into the future. So this is the first part of the circuit. This is what you call the transient. Okay, the transient response of our circuit, because it's transient, it's changing. All right, and this second part where you have a relatively straight line at this is I. At I equals IS or I infinity, this is the steady state. Steady state and transient. So we're going to use this conceptual understanding to derive the formula for the step response RL circuit. So we know that I, as a function of time, is going to be I transient plus I steady state. All right, that's settled. I transient, the transient current, if you remember from the source free RL circuit, is going to be a constant. Let's call it A times e to the minus t over time constant. All right, this is our current. Very simple. Oh, okay. I transient, not I of t. Okay. I transient. And I steady state, the steady state current, is going to equal look at this, is a steady value, alright? This is a simple straight value. So that means at t equals infinity far into the future, our inductor is going to resemble a short circuit, alright? Going to resemble a short circuit, the short circuit fault. So something like this. Okay, and there's no voltage across the short circuit. So that means the only element here left to partake in this voltage is going to be R. So that the current, steady state current, is going to be Vs over R. So putting this together simply, we know that I of t, the current as a function of time, is going to be AE minus t over tau plus Vs over R. Okay, which is really, really close to the formula. But the work we have to do now is to find out what this A is. Okay, this constant for the transient current. What does this signify? And how we're going to do this, we're going to say, all right, let the time equal 0. Okay, let me solve this somewhere so we can get a bit clearer. So we're starting off with I of t is equal to A e to the minus t over time constant plus Vs over Vr. Okay, so setting time equals 0. Okay, looking at this when the time equals 0. So I of 0. We call I of 0 is the current at time equals 0. And this, since our inductor is charged with an initial current I naught, this is our initial current. Okay, that means I of 0 is going to equal I naught. Hope that's clear. So I of 0, the current at time equals 0, is going to equal I naught. Is going to equal A e to the 0. Okay, because you have minus 0 over time. So this is going to cancel out. Let's erase that. A, so that's A on its own, plus Vs over R. So simplifying this and making A subject of formula, we're going to end up with A is equal to I naught minus Vs over R. So what we have to do now is substitute this into the formula, into what we had here originally. So we're going to have I of t, our current as a function of time, is going to equal I naught minus Vs over R times e to the minus t over time constant plus Vs over R. Okay, usually this will come before the bracketed exponential, because you have steady state and transient, so just so it looks prettier. And what we're going to do now is we're going to make this substitution that the current, that's the current at the source, is going to be Vs over R. So we're going to substitute this for Vs over R in our formula. So that's going to give us, and rearranging, bringing this forward, is going to give us I infinity plus I naught minus I infinity e to the minus t over time constant, and this is all in amps. So there you have it. It's a really, really elegant derivation for the step response of an, let me make this correct, the step response of an RO circuit, much shorter than that's for RC. But you see, if you recall the formula for the RC circuit, is essentially it's still the same format, because V of t is going to be V infinity plus V naught minus V infinity e to the minus t over time constant. So this is for step response RC, and this is for step response RO. Which I hope this helped.